Okay, so starting from the 4-bit sequence 1101, what are the following 4-bit counters after each clock cycle until the sequence repeats? Okay, so a ring counter. So the way a ring counter works is the last bit comes around to the front. So this last one comes to the front, and the other 3 bits shift to the right. So this comes to the front, and the other 3 bits shift to the right. Comes to the front, and it shifts to the right. It comes to the front, and shifts to the right, and now we're back to where we started. A Johnson counter acts in a similar way, but when it goes to the front, it toggles. It becomes a complement. So this 1 comes to the front, but then it becomes the not of what it was. So it becomes 0, 1, 1, 0. And then this 0 comes to the front and becomes the not of what it is, so it becomes 1, 0, 1, 1. And then the 1 comes to the front and becomes a 0, 1, 0, 1. And then 1, 0, 0, 1, 0. 1, 0, 0, 1. 0, 1, 0, 0. 1, 0, 1, 0. And 1, 1, 0, 1. So that's a ring counter and a Johnson counter. Yes.
So the Johnson counter does what the ring does, but you just not the first number.
You not exact. Well, you not.
What tone number?
Yeah. Yeah. And then an up counter does exactly what you would think it does. It just counts up in binary. So this number in binary is 13. But the next number would be 1110, which is 14, and then 1111, which is 15, and then you go back to 0000, then 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1000, 1001, 1010, and 1011, and then 1100. So that's an up counter. It just counts up. Yep.
Do you go only to 12, or do you go all the way back to 13?
It would keep repeating. Well, the only reason I did is said the problem said until the sequence repeats. But in general, a counter would just keep going until you told it to stop. So it wouldn't stop anywhere unless you gave it specific instructions to stop. So it would just keep going and going and going and going. And then a down counter is going to just go the other direction. So it would start with 1101, 13, and then 1100, and then 1011, and 1010, and 1001, 1000, 0111, 0111, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, yep.
For the up counter, is the reason why it went to 0, 0, 0, 0 is because it's a 4-bit. What if it was an 8-bit? It wouldn't have been there.
As an 8-bit, it would just keep counting until it got to 1, 1, 1, 1, 8 times. Yep. I'm counting down. 0, 0, and then 1, 1, 1, 1. And then 1, 1, 1, 0, and 1, 1, 0, 1. Is that where I started?
Yep.
Yep. So that was just counting down. And if you are given something and told that it's a counter, you can expect it acts as an up counter. You don't have to do anything to make it count. You can just expect that this is what it does. Unless it tells you it's a ring counter or something like that, which I doubt. What you would more likely see is something like C here, or B, where you have to do it yourself. So it says, using a 4-bit synchronous up counter with parallel load and a minimal number of additional gates as needed. Design a circuit that counts in the sequence 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11. Okay, so this one, we want to do this. So you have a counter. And it has outputs Q3, Q2, Q1, Q0. And it has inputs, how are they labeled up here? D. D3, D2, or did they do them with starting with 0? They did. They did them starting with 0. So that makes it kind of weird, but so assuming that it'd be the same way, 0, 1, 2, 3, 0, 1, 2, 3, and you have a load. And I'm not going to worry about the clock and the enable, but you have a clock and you have an enable, but I'm not going to worry about that. Okay, so it says it has a parallel load. And what that means is when the load is equal to 1, it loads the value that's on these wires. So we want it to start at 7. So with 4 bits, 7 is 0, 1, 1, 1. And this is bit 3, bit 2, bit 1, and bit 0. So we want to load a 0 onto 3 and a 1 onto each of these. And we can assume that once we've loaded it, the output it's going to give us 7, and then it'll give us 8, and then it'll give us 9, and then it'll give us 10, and then it'll give us 11, and then it would give us 12 if we didn't tell it to stop somehow. So, because it's a counter, so we want it to stop at 11. So if we want it to stop at 11, we want it to stop when we get to 1011. 1011. So this is Q3, Q2, Q1, and Q0. So when it gets to that number, we want it to stop and load 7 again. So when Q0, Q1, and Q3 are 1s, so Q0, Q1, and Q3, when those are all 1s, that's when we want it to load. So we'll AND those 3 together, and put that into the load. And so when those are all ones, it'll load 7. Because whenever that load is 1, that's when it'll load. Now, we don't have to put that Q2 is 0 in this case. If we had some sequence that wrapped around, like if we wanted it to count 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 1, 2, 3, then you probably have to put the 0 in as well. You put a not in there. Putting that in doesn't hurt anything, but it's not the most efficient. And the problem said using a minimal number of gates as necessary. So since we're not wrapping around, we don't need to put that 0 in there.
Why are you loading in Q2 and not, Q3 and not Q2? Are you loading in 11 first?
I'm checking for 11. I'm not loading 11. So I'm checking for 11. So load, this value is either a 1 or a 0. And when Q3, Q1, and Q0 are 1s, that is the number 11. And so I'm checking for 11. So if these are all 1s, the AND of that is 1, and load will be 1. At any other time, the AND of these 3 is 0, and it won't load.
So what does a load do?
Load says load these values.
Oh, okay.
And so it would load 7, and you'd have to start over with 7.
So we have one account from 7 to 11, and so we found like the decimal number that is 11, the binary number that is 11, and then we plug the values like Q3, Q2, Q1, Q2, and then we look at where those values are 1, and those are the values we put like in the AND gate, which goes to a load.
Yep.
So that's saying stop at 11.
That's saying stop it. It's saying at 11, load the values that I have lined up to be loaded, which is the number 7. Other questions? All right. So this is probably the hardest one. Is the most recent one. Yeah.
Did we do part C?
Probably not. Nope. But now we know how to do it. So this one has a 1 on the enable. So that's just saying, yes, it's enabled. And then it's loading the value that has D0, 0. So let's write this out. This is D0, D1, D2, D3. So this is 0, 0, 0, and 1. So that's the value 8. So it'll start counting at 8. And it'll stop whenever Q1, Q2, and Q3 are all 1. So let's see. So we have, at 8, we have 1, 0, 0, 0, and then 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. So I'm looking for 1, 2, and 3. 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. So that would be at 8 and 4, 13? No, 14. 14. Yes.
Since Q0 is not plugged into the load, does that automatically make it a 0, or does that just not matter?
It means we're not looking at it. So it doesn't matter. So I could have messed myself up if I had chosen the wrong wire to draw in on this, because I just took the sample test and just picked one to draw in to make it different from the one on the sample test. And so if it had wrapped around, I might have ended up with something different, because, yeah, it just ignores it. If I wanted it to be equal to 0, I'd have to put a NOT gate on it and put it into the AND.
So it could possibly still be a 1.
It could, but we're not going to get there with this counter, because the first time we get to all these, that's why I'm saying I could have messed up. I could have made that happen by accident, but the first time we get to all of these being 1 happens at 14, so it is not going to ever do that. But it's possible I could have, like if I had started not at, I don't know, I'd have to think about it, but there'd be a way to do it.
Thank you.
Mhm. Yes.
If they want us to do, like for B, if they want us to do instead of like an up counter, like a Johnson counter, how would that change? That we would have to like this.
I doubt they'd give you that because you've never had a homework problem like that. You could have a down counter. Down counters would work the same way. You could figure that one out. You just count down instead of counting up. But I doubt you'd have a Johnson or a ring counter because that would depend on your that one's not predictable because it's different for depending on your starting number. With an up counter or a down counter, you know where it's always going to go because you know how the numbers count. So I doubt you'd have a ring or a Johnson. Yeah.
If it were a down counter,
Uh-huh.
would you go backwards from the B's, or would it still be 1,000?
It would still start. These would still be the same order, but rather than, so if it was a down counter, we would still start with 1000, but we would go down to 0111, 0110, 0101, 0100, 0011, 0010, 0001, 0000, 1111, and then it would stop because, as you said, it's not even looking at this one. So it would stop, and then it would load 8 again.
Thank you.
So the counter would look the same. It's just how it gets there is different.
Yeah, it would just say it's a down counter.
So it would still look like when we drew it, it would look the same thing. It would just be a down counter.
Yeah,
So why would the down counter stop at 15?
because we were looking for where Q1, Q2, and Q3 were all ones. And so when I get to here, they're all ones.
Okay.
So for number 2, it says, what is the last count before the load happens? So does one tell us like number 14?
Yes.
Like,
Yes.
So we can just look at the right side of the counter and answer it. Because
Probably as long as the left side, so if it's, let's say it's an up counter, and the left side is 5 and the right side is 12, yes, as long as this number is bigger than this number. If this number is smaller than that number, you better check it, because something weird might be going on with the bit that you're not checking.
right, because on that one it didn't end, like the right side wasn't a
It was
Okay.
not 1110.
right.
Yeah.
Could you put a knot on Q0
Yes.
for it to keep counting back to 14?
Yes.
So up counter, left and right, down counter, check it essentially. Because if it was a
No. If an up counter, if it's the number you're ending with is bigger than the number you're starting with, and with a down counter, if the number you're starting with is smaller, I mean, if I went 12 to 5, you wouldn't have to check it.
okay.
But it's when you have to wrap around that you need to be careful.
If it was a down counter from 7 to 15, it would look different between that and the up counter. Because if you added all of them like we did, it would just stop at
Yeah, so I will be honest with you. So from what I've seen, the professor you have and the professor who that uses the same notes and tests and homework has never wrapped around. But there is another professor who does.
Okay.
And so that's why I'm used to doing this. And so I think you'll probably be fine just checking the ones, because I've never seen them give a problem where you'd have to worry about it. But I have seen it in other digital logic sections. So, so I just worry, you know. But I think you probably are fine just handing the ones. I've also don't think I've ever seen a down counter on a test, but I don't want this to be the first time. Okay. All right. So problem 5, you're given the state table below and the state assignment D equals 0, 0, E equals 1, 0, and F equals 1, 1. Construct the state assigned table, assuming D flip-flops, where the state assigned table will have the following headings. So this is actually really easy, and I don't want anybody to miss this. So present state, next state, W equals 0, W equals 1, output Z, and we have Y2, Y1, and here we have capital Y2, capital Y1, oh, I have this written twice, but that's okay, W equals 0 and W equals 1. All right, so we have our output is 0, 0, 1. That stays the same. D, we are told, is 0, 0. So everywhere where we see a D, we put a 0, 0. E is 1, 0. So everywhere we have an E, we put a 1, 0. F is 1, 1. So everywhere we have an F, we put a 1, 1. And then to do the next part, to get my minimum Boolean expressions, and that's all there is to it. But to get our minimum Boolean expressions, I am going to want to have all of my possible values. And I'll want to have them in order just because it's easier to read. And so this next part is really, this is just going to be a little bit of notes to make things easier for me. So we'll have 0, 0, 0, 0, 1, 0, 0. That's just copied straight from here. Our next state is 0, 1. That's not in here. That's going to be don't care, don't care, don't care, don't care. And then I have 1, 0, 0, 0, 1, 1, 0, and then 1, 1, 1, 0, 0, 0, 1.
How did you get the don't cares there?
Because there is no state 0, 1,
Oh, okay.
and so those are don't cares. Now, to get my expression for Y2, I'm going to have a Carnot map that has Y2, Y1 on top and W on the side. So y2, y1 to be 0, 0, 0, 1, and then on a Carnot map you do 1, 1, 1, 0, and 0, and 1. So W equals 0 is, this is y2. W equals 0 is this column right here. So this part refers to W equals 0. This part refers to W equals 1. The first column is y2, and that's the first column in both of these is y2, and the second column is y1. So if I'm doing y2, so right now I'm interested in the first column. So I'm interested in these values and these values. And the left-hand circle is when W equals 0, which is right here. And when y2, y1 is 0, 0, and W is 0, y2 is 0. When y2, y1 is 0, 1, that's right here, and W equals 0, y2 is don't care. When y2, y1 is 1, 1, and W is 0, y2 is 1. And when y2, y1 is 1, 0, and W is 0, y2 is 0. And then I get the values for when W equals 1 from this second group over here. So when W equals 1, which is over here, and y2, y1 is 0, 0, I have the value of 1. When y2, y1 is 0, 1, and W equals 1, I have a don't care. When y2, y1 is 1, 1, and W is 1, y2 is 0. And when it's 1, 0, and W is 1, I have 1. So then I'll have my Carnot map. Let's see, so I would get these and this. So y2 is going to equal, that top group is y1, or, no, it's y1 w bar, or the bottom group is y1 bar w, which, if you wanted to be like extra sneaky, is y1 exclusive or w. So if you have x, y bar, or x bar, y, that's x exclusive or y. Okay, so now to get y1, I'm going to do the column that I do not have circled. So y'all see if you can fill this one in. Yes.
On the exam, since it's technically the minimum cost expression, would we have to put an exclusive or?
I doubt it.
Yeah, I feel it. I don't
I
think we
doubt
ever
it.
had to do that, like on like a, on a homework or anything.
She's never told us anything about it.
I doubt it. Again, it's something that I have seen, but I don't think you would have to. Okay, so I see that y1, if when I'm looking at this, when w equals 0, I see they're all zeros except for that don't care at 0, 1. So I'm just going to put a don't care at 0, 1 and put zeros in here. And then for w equals 1, I still have the don't care at 0, 1, and I've got a 1 at 1, 0, and I've got zeros at 0, 0, and 1, 1. So it looks like this one, y1, is y2, y1 bar w. And then our output doesn't depend on w, just depends on y2 and y1. So 0, 1, and 0, 1. And at y2, y1 is 0 and 1, I have a don't care. At 0, 0, I have a 0. At 1, 0, I have a 0. And at 1, 1, I have a 1. So I get my output z is equal to y1. Couldn't we just make the right shift backwards, like invert the order? You could invert the order to the flip-flops. I just don't like doing that because I am used to having my least significant bit in the front. But I don't see why you couldn't do that if you wanted to, except, I mean, you could. Yes.
There was something more we had to do after we found the expression. But did
Let's
she
see.
say that she was gonna leave
Derive.
that for the font?
Like the circuit?
She
Yeah.
said,
Oh no, she's doing the state diagram for the final.
right, and I did not do a state diagram because she told me that, so I left that one out.
We will have to probably draw a circuit though, once we have the 3 equations. I assume.
Well, the old test had you did not have to draw the circuit.
Okay.
Yeah, but I mean you can. That's easy to do once you have this.
Yeah.
Yeah.
Is that how do you do that?
Okay, so I'll
Pretty
show you.
different.
No, okay, so no, let me show you. So here's how you would do this. Because you're not, okay, so okay, so y2 equaled y1 w bar or y1 bar w, or I'm gonna, because I don't have much room, well, I'm gonna do an exclusive or, but you could also do all those gates. So I'll do all the 8s. Let me just copy these down. I need more room. Can someone just tell me what Y1, Y2, and Z are?
Expression.
Yeah.
I can do it.
Okay.
Y2 is equal to Y1 and W naught, or Y1 naught times W.
Okay.
W. And Y1 is going to be Y2 and not Y1 and W
Or W
and W.
and W. And Z was,
Should be like,
Z is Y1. Okay, so we have 2 flip-flops. This one's Y1. This one's Y2. I also have Z. Z is Y1. So that's Z. D, Q, D, Q. So if I have Y and I have W over here, so if I have Y1 and W naught, and Y1 naught, and W, and then I OR those together. That is actually Y2, not Y1, sorry. Y1 is Y2 and not Y1 and W and then Y1 is Z. So that's how you would draw the circuit. So actually that was worth doing, and I had forgotten about that, because I could see that being, even though this problem, the old test didn't have you draw the circuit, since she's not having you do a state diagram, she could have you do a circuit. So, any questions on that? So, any final questions? Because that was the end of what I had, and it is actually exactly 6:30, so that's when I said I would be done. But I am happy to answer any other questions if you have any. And
Can you re-explain the chart?
yes,
Filling in the numbers?
I will. Let me post the first part of the recording first, and then I will do that. You want me to explain the hard part?
The filling in the chart with the zeros, like filling in the K maps from the chart.
Yes, yeah, okay, yeah, that is the part, that's the part that people always, yes, that's the hard part, that's the part people always ask about. So, do you mind if I just do a different one over here, just for an example? So let's say I have, this is my, my chart. Okay, so I just made a different one up. Okay, so then the way you do it is these two columns right here. This, the way I have it labeled, this is Y1 and this is Y0. And this is Y1 and this is Y0. And everything for this column is when W equals 0, and everything for this column is when W equals 1. And these are the values that I'm actually going to put in my K-map. So if I'm doing a K-map for, let's just do one for Y0. If I'm doing a K-map for Y0, then the values that I'm going to be using are the second column here. And then how I figure out where they go is like this. So this is the W equals 0 row. So the values for Y0 in this row are going to come from this group right here. And how I know where to put them comes from this label at the top. So 0, 0, that's this one. And I'm doing Y0, so it's this one right here, and that goes here. So what I'm matching up is I'm getting my value from inside here. This is telling me which column. And the row comes from, this is from W equals 0, and this is from W equals 1. And so, like, let's say I wanted to fill in this box right here. That would be from 1, 1, when W equals 1, and then because I'm doing Y0, it's going to be this value right here. So that one would be 0. So can you tell me what would go in this box? D. Yep. I think you thought I was asking a question, and I wasn't. I didn't know. I didn't mean to be asking a question. Did I have it here?
No, you had it under the D.
Okay. Yes. And yeah, that one would also be D. Yeah. Yeah. So what if I was doing Y1, and I wanted this one right here?
Zero.
0. Yeah. And did you get it from right here? Oh, okay. This is the output. Yeah. So Y1 is the first number.
And it's 0. W is 1, so you look off.
I'm looking at this group right here. And then because it's Y1, I'm looking at these numbers. So you have to match up all of those things. You have to match up Y1, W equals 0, and that, and then get the value from inside there. You're welcome.
I have a question about the circuit.
Yes.
So Y2 is equal to Y1 and not W, but you took the wire from Y2.
I think it was whenever you switched them, like you already started working it and then realized that they were flipped.
I don't need you to change it. I just want
Yeah,
to make sure it
that-
comes from
yeah.
Y1. Okay.
Yeah, that's yeah.
I think I ran into the same thing when I
Yeah.
was doing
Yeah, I just wanted to make sure that I was.
Now, anybody watching this is not going to wait till the end and find that out. I'm going to have to put that in.
it. Hopefully they see it and get confused and then like, okay, well maybe she realized.
Yeah.
Send an email.
Yeah, that's a good idea.
The,
Yeah. This,
whenever-
yeah. So like this circuit right here, when I switched my Y1 and Y2, I messed it up because Y2 is Y1 W naught. Or Y1 naught W.
And I can read out the other ones if you want. Or are you just redoing
I'm just redoing it.
Okay.
So I'll make, I don't know what I had. I'm gonna make Q bar, Q bar. So W. So Y2, which is down here, is Y1 and W naught and Y1 naught and W, and those are ORed together, and that's Y2. And Y1 was Y2, Y1 naught, YW. Y2 Y1 naught and W, and that's Y1. And this was Z. Okay. All right.